Today we are going to be calculating averages and kind of reviewing what it looks like to calculate an average, and then apply that to average atomic mass so that we can calculate the average atomic mass given the mass and how many of them there are in a sample. So let's start by just kind of reviewing what an average is. So when we find the average, you will take the total sum of whatever it is you're working with, and then you'll divide by how many there are, the number of items present. And one way you can find the total sum is just add up every single value that is present. Or if you know how many of each value there are, you can use some multiplication to help you so you don't just have a long line of addition. So you could take your number count times the value it represents, and do that for each value that there are. And then divide by your items. So that's just a way to show the total sum. Take how many there are and the value it represents for each value, and then divide by how many. So let's actually apply that so you can see what I mean by count times value. Just using some examples that we are pretty familiar with. So average grade. Let's say there are 20 kids in a class. Here are their grades. And each grade has a specific value or points that is going to be associated with it. We want to know what's the average grade in the class. So using this second form here to find the total sum, we could add 50 points plus 60 points plus 60 points for the 2Ds, and then 70 plus 70 plus 70 plus 70. You get the point, right? It's a lot of addition of the same number, so why not use multiplication and make our lives a little bit easier? So the way we can do this, we've got our count. There's 1, and the value for F is 50. Then we have our 2 count for value of 60, that's our D. Then we have 9 C's, which is a value of 70, plus 6 B's, a value of 80, and 2 A's, which is a value of 90. Then we divide by how many there are. There are 20 grades. So if we put that into our calculator, we get 75 points is the average grade. When you put this into your calculator, you will want to use a scientific calculator that has parentheses that you can use, and then you can put it on as one string using parentheses. So if we were to put this information into a calculator, I'm going to write it up here for how to do this the fastest, most efficient way. So you're going to want to group each of your multiplications. So put a parentheses and then do your first multiplication. And then you can just add the next one, 2 times 60 plus parentheses 9 times 70 plus parentheses 6 times 80 plus parentheses 2 times 90 equals. And if you do it this way and you show the groupings, you will get 75 just by typing that into your calculator. If you try to just do 1 times 50 plus 2 times 60, you're going to get wonky numbers because your calculator doesn't know you're trying to group certain things. So put it in your calculator like this when we're calculating averages using the count times value equation. Now let's do another example using average weight. A wrestling team wants to know the average weight of a player on their team. This time, instead of giving us an actual count, they're giving us percentages. And a percent is always out of 100. So we're going to say that the team is 100 players. They didn't tell us. That makes it much easier to figure out the count. 5 players are 5%, 10 players is the 10%, 45 players, and 40. They become our count, and then our total number that we'll divide by at the bottom is going to be 100. So let's do the work for this, starting with our first count. So we have 5 of the 100 with a value of 135. Then we have 10 with a value of 145. Then we have 45 with a value of 155 pounds. And lastly, we have 40 with a value of 165 out of a team of 100 players. If you put this into your calculator, this time I wrote it in that calculator form, putting them in groupings, then you will get the average is 157 pounds. Now, this should make sense because the most percentage on our team was around 155 pounds, 45%. So the most percent abundance, these are representing percent abundance of each weight. The largest percent abundance is going to be the closest to your average. 155 is closest to 157. So these are percent abundance, that's what we call it. How abundant is each one? And when we see percentages, that just means our total is going to be 100. Now let's bridge this over to atoms. So we have 3 isotopes, which just mean variations of the element oxygen. They're going to have different masses. We've got oxygen 16, oxygen 17, and oxygen 18. Remember, these are isotope names, and we have the element name with a dash and then the mass. That's what this number is, mass. And that's protons plus neutrons, if we were counting them. Now, for our calculation of the average, we're going to do the same exact process that we just did for average weight, but using it for the mass of the atoms. So our count is going to be out of 100 since we have percent abundance. Again, this is called percent abundance. And our count for oxygen 16 is 99.7. What is our value? Well, we're trying to find the average mass, so our mass is going to be our value, 16. And we're going to do that for each isotope. So our next count is 0.2 times 18. And our third one, 0.1 times 17. Don't forget to divide by how many there are. Since this is percent, that'll be 100. And calculate. This comes out to be 16.00 for our average. The units for average atomic mass and particles are atomic mass unit, AMU. We talked about that in part 1 of our subatomic particle notes. AMU are just really, really tiny mass units for atoms instead of trying to talk about it in terms of grams, which would be so microscopic it wouldn't be helpful. So AMU is what we use. And so there is our average atomic mass. And again, the highest percent abundance should match your average the closest, and it does. Another kind of cool thing about the average atomic mass is that if you pull up the periodic table and you look for oxygen, you'll find the average atomic mass should match this number here, maybe with a little rounding error, because it's taking into account all of the different isotopes that exist of oxygen and averaging them out. That's actually how they figure out the numbers that go at the bottom of the element square. They take the percent abundance of each isotope and use their mass to then calculate what the atomic mass units of that average atomic mass would be. So it should match the periodic table. When working through these problems, you're going to be following that same process. So number 1 is exactly like what we just did for oxygen, so I'm going to leave that for you. Number 2 is exactly like we did in the example with a change for A. It says, what is the most common isotope of chromium? Most common means highest percent abundance. So our highest percent abundance is 83.79. That is chromium 52. So that would be your part A. Part B, follow the same process, doing your count times your value for all of the isotopes divided by 100. Finn is working in chemistry lab where he identifies 2 isotopes in an unknown element sample. This one's a little bit different, so we're going to do this together. 60% of the atoms have a mass of 68.926 AMU, and 39.89% in the sample have a mass of 70.925 AMU. What is the average atomic mass of this element? Same process. We have percent abundance, that's our count, times the value, there's our mass, 68.926, plus, now we have another count, or percent, just out of 100, and our mass. Then divide by 100, since this is percentage that we used, and we will get the average atomic mass. So this part is very similar to what we've been doing. I get 69.72 AMU. The second part is where it's a little bit different. It says use your periodic table to determine its identity. Go into your periodic table and see if you can find an average atomic mass that is closest to 69.72, and that should be the identity of this element. I'm going to let you do that on your own. Number 4 says, in a sample of 16 hydrogen atoms, there are 4 atoms of hydrogen 1, 4 atoms of hydrogen 2, and 8 atoms of hydrogen 3 as pictured below. So this would be hydrogen 1, this would be hydrogen 2, and these bigger ones are hydrogen 3 in our sample. What is the percent abundance of each isotope? Hint, think about using fractions. When we find percent abundance, it's always been an amount out of 100, but in this case we have 16 total. So I have, for hydrogen 1, 4 out of my 16, which ends up being 0.25. What is that in percentage? That's 25%. So we have 25% abundance of each one. You do hydrogen 2 and hydrogen 3 using that same thought process. Then you'll calculate the average atomic mass now that you have percent abundance and mass of each. And then you can take a look at the element square of the periodic table. You'll see that it's significantly different than what we did in this example. Hint on that, our sample size is super tiny and it's not representative of the true ratio of hydrogen 1, 2, and 3 to each other in nature. So that should help you explain why they're different. That is our math skills for today, finding average atomic mass.